Welcome back to the Tech Civil Learning. My dear friends, I promised you just give me your 20 to 30 minutes time. You'll surely going to understand the concept which is mentioned in the thumbnail. So without wasting time, let's start the today lectures. So please watch the video till last so that you can understand the concept very clearly. In today's lectures, we will discuss about the analysis of the flanged beam, right? As we have already analyzed, we have already analyzed L sections. We have already analyzed what you call singly reinforced beam, doubly reinforced beams. So in today's lectures, we will analyze the flanged beam. Hope you have seen my previous video. What do you mean by flanged beam? Why we are always taking effective with the flange? So if you have not gone through that one, please understand what do you mean by flanged beams from the previous lectures so that it will be very helpful. So here's neutral axis means within the flange portions, right? When the neutral axis is within the flanged portions, right? Let me tell you first things. The neutral axis lying does not depend on your hand. Yeah, it may depends when you control the width of the beam, right? Dimension of the beam, then it may be in control, but the what you call the position of the neutral axis always depend upon the thickness of flanged, right? Depth of beam, right? So the amount of steel used. So if you increase or decrease the depth of the beam, then it may be in your control, but the neutral axis always depend upon the thickness of flange and the width of the beam. So let's analyze the when the neutral axis is within the flanged portions, right? Here in conditions 1 we have assumed that the neutral axis is within the flanged portions. So my dear friends, this is stage sections I have taken, right? So I have here inserted a reinforcement steel bars HYST or as per the required, right? So from here to here, right? From here to here it is nothing but the D, that is effective depth. From top to bottom, from here to here is nothing but the D, that is gross depth or overall depth. From here to here, that is we have considered the effective width. Why we have not considered the actual width? I have already told you the reasons. So this one is verticals depth of flanged. So let's analyze this ones, right? So I have told you that the neutral axis lie within the flanged. So considers this one is neutral axis, right? Means NA. So this one is neutral axis. So here as you can see, this one is a neutral axis, right? So what I have did, I have make here a stress block diagram, right? Hope you have seen the what do you mean by stress block parameters at stress block diagrams. So as you know, as per the assumptions of the flexure, right, we know that it will follow parabolic till 0.002, right? So somehow imagine these ones up to here it will follow parabolic, right? 0.002, right? Up to 0.002 it will follow the parabolic, and after that it will be constant and it will form a rectangular shape, right? So these ones, so we know that we have already analyzed the rectangular sections, right, in the previous lectures only. So here the formations of the parabolic as well as rectangular shapes. So this one is the what you call compressive design strength, right? 0.446 FCK is the compressive design stress. So my dear friends, this one, suppose imagine the neutral axis lie at this point, right, and the total stress, total compressive force induced in this one is given by 0.36 FCK BXU, right? In the previous we have already derived this ones. 0.36 FCK BXU is the total compressive force, right? We have already derived. So for these ones, as it is flanged, so what will do, 0.36 FCK BF into XU. So this one is the compressive force in the topmost flanged. So here for and this ones for the tensile force, that is 0.87 FYAST. So this one is very simple, as because it's completely depend upon the rectangular sections, and we have already derived these ones. So let's see if in first steps we will need to calculate XU limit, and XU limit is nothing but the K into D, where K is neutral axis constant, right? 0.48, right? For FE 250, for FE 415, for FE 500, the K values vary. So you will get this one from the code book itself. So in the second steps we will calculate the means XU, right? XU is the means bending moment, right? Means actual bending moment. So that can be calculated by equating C is equal to T, where the C value is from here and the T value is from here. So if you equate from these two, we need to calculate what? The neutral axis depth. So neutral axis depth 0.87 Fy. This one is the formula of neutral axis depth. You get this formula in page number 96 of iOS codebook 456. Either you can means directly equate 0.36 FCK BF XU to 0.87 FY AST. From here you will get the means XU value. So in step 3, in step 3, if you compare XU and XU limit, then means if XU is equal to XU limit, if both are equal, then that will be balanced sections, right? That section is balanced. If XU is less than XU limit, then that will be under reinforced sections. If XU is greater than XU limit, then that will be over reinforced sections. So in steps 4, the main theme of this one for analysis, we need to calculate the moment of resistance. As I have told you in the previous, we have also already analyzed the singly reinforced beam, doubly reinforced beam. So the main theme is to find out the moment of resistance. So moment of resistance for the compressive, right? Moment of resistance is nothing but the means verticals. Either it may be means moment of resistance can be calculated in compression zone as well as in tension zone. So the moment of resistance MOR is equal to force into lever arm. What? Force into lever arm. So force, the compressive force 0.36 FCK means here will be BF XU, and this one is the lever arm, right? This one is the lever arm. Hope you understand what do you mean by lever arm. If you have forgotten, let me tell you one more thing, right? If suppose imagine the hair, right? The means verticals. Wait, my dear friend. Support CG, right? CG of means this diagram, right? Means vertical CG of stress block diagrams lie here, right? Imagine CG of this diagram lie here, then here to here, right? The distance between CG of the stress block diagram to the center of the means steels, that is nothing but the lever arm. And here means this one is means verticals. The total is D minus. Here we have already calculated from the stress block diagram in the previous lecture only. The distance between here to here is 0.42. So that's why we have deducted D minus 0.42 XU. Right. Hope you have seen my previous video, so that makes you means easy to understand, right? So here MOR means for that in the tensile zone. So 0.87 FY AST into what? Lever arm. So lever arm is D minus 0.42 XU. So these ones is means when the neutral axis lie in the flange sections is completely based on the rectangular sections which we have already discussed. So there is no need of any complications, right? Means this is not a complex types. So hope you have understand the clearly. So let's see the conditions too, right? Means when the neutral axis lie in the wave portions, there is chances of lie in means flanges. If it is lie in wave portions, then what happens? So it means hope you means can understand these figures, right? This is means actual, this one is effective width, right? This one is the effective depth. This one is the neutral axis, right? This one is the WB, that the width of wave, and this portion from here to here, that is total BF minus BW. This BF minus BW, then you will get this portion. Similarly BF minus you will get these portions divided by 2, right? Because the total is means these two portions, then if you add all these things, then you will get BF, right? Similarly the depth of this one's flange is DF. So let's understand this concept, right? So from here it is neutral axis. So a stress block diagram is always initiated from the where? Neutral axis. So here I have initiated a diagram, right? From up to 0.002 it will follow parabolic actions. After that it will be constant and form rectangular block, and this one is parabolic block. So from top to up to neutral axis it is what? Neutral axis, the depth, that is XU, and from means 0.002 to above, that one is 3/7 XU, and from down 4/7 XU. We have also derived 3/7 XU, 4/7 XU in the previous lectures only. So if you are continuously following my lectures, hope you have understood So here that means compressive strength stress is 0.446 FCK. So this one is diagrams. What here I have means what I have here did, that I have just separated these two figure, right, means wave, right, this one is wave. So this one's suppose one, this one is wave figure 1. So I have means separated these figures here clearly. So this one is figure 1, right, figure 1's the effective depth, and AST 1's, right, this one is BW, right, and here is no space, so that's I have drawn the second figure, that is the flange figure. These ones flange figures in the downward by removing this means wave. So let's understand when the flange is uniformly stressed, right. Here in the means when the neutral axis lie in the wave, there may be two conditions: when the flange is fully stressed, when the flange is when the flange is uniformly stressed, when the flange is not uniformly stressed. Then what do you mean by uniformly stressed types of flanged? Right, means of course there means we need to know what do you mean by uniformly stressed flanged. So let me tell you, my dear friends, as you can see, this is the means what depth of flange. As you can see, the depth of flange is totally lies, right, in these sections only, right, means this width is completely means what you call immersed in these sections only, right, means the depth of flanged, right, this one depth of flanged means is continuously immersed in the rectangular sections only, right, rectangular distributions stress only. So that type of means flanged is uniformly stressed. If these types of flanged lie means some portion is parabolic and in some portions in rectangular, then that type of flange is non uniformly stressed. So as it is completely lie in these sections in the means what you call rectangular stress block only, so this is nothing but the stress uniformly stressed. So let's analyze the figure first, right, from wave. So from figure first we have already calculated C1. C1 is the compressive force, right, and hope you know compressive force is equal to means stress into what area. So stress 0.36 FCK, right. So this one's area of this first sections is, as you can see, the area of the first sections is this one's, right, means this much area, that is 0.446, and means this one is XU, right, this one is XU. So as a rectangle sections, here to here is 0.446 into XU. So 0.36 is the stress and BXU is the area. So 0.36 means FCK, and the B here, B can be written as BW because we are calculating for the wave. So F3, most of the students are doing wrong here only, right. So means always remember that if you are means analysis of the means what you call the flanged beam for the wave, then we must means substitute WB instead of WF. So 0.36 FCK means BW into XU. So this one is the means total means what you call compressive force for this means figure 1. Similarly T1, so 0.87 FY AST1 total tensile force for the sections or for the figure 1. Similarly lever arm, hope you know how to calculate D minus 0.42 XU. So the moment of resistance will be the same as from the means what we have did in the means for the means neutral axis lie in the flange. So same formula, just the difference is instead of means F, here the W is substituted. So 0.36 FCK, W means BW, XU means of D minus 0.42 X means XU is a compressive for the compressive zone. Similarly for the tensile zone 0.87 FAS to D minus 42 is the for the tensile zone. Now we need to see figure means what equals 2, right, just means here up to here we have just analysis for the figure 1 only, right, as it is the combination of two figure, that is flanged and means for the wave. So we have to analyze both sections, right. So considers the two figures, right, this one is wave, right, and in middle of this one is this one is flanged and the middle of this one is wave. So we have already calculated for the wave. So here we will just calculate for the flanged. So BF minus BW, right, BF is the totals this ones and BW you know this one, this flanged we have means we have removed this one's flanged, so minus B means BW. So here's this one is DF. As you know, for analysis we must means satisfy C is equal to T, right, C is equal to T. But what happens in this ones, here is no reinforcement, so we will assume that we'll provide reinforcement at the bottom so that it can satisfy C is equal to T conditions. So this one is imaginary line, right, imaginary, and here I have substituted AST2, right, means AST2. So this one is lever arm, as you can CG, right, lever arm always taken from CG, right. So here the CG value will be half of these ones, df by 2. Of course center of gravity always lies at the center of the section, so df by 2. So from here to here is the what you call the reinforced lever arm 2. So now we will see C2. So C2 is equal to 0.446, right, as you can see from the above, right. 0.446 means what? Compressive stress, compressive strength of stress, or you can also say design compressive stress. 0.446 into area, right, area of this one is BF minus BW into what? DF. So these ones, right, area into what you call stress. Similarly T2 0.87 Fy AST2. Similarly lever arm will be D minus DF by 2. Here the CG lie at a point DF by 2. So D minus DF by 2. Now similarly we will find out the moment of what you call resistance. So moment of resistance is nothing but 0.44, that is what you call the compressive force into lever arm, right. The compressive force we have already calculated, just we will multiply with the lever arm. So here into D minus DF. Similarly for the tensile joints, right, for the tensile joints tensile force into lever arm. So 0.87 Fy AST2 into, right, D minus DF by 2, right. For the analysis of T beam, then we must have to add section 1 as well as 2, right. We must have to merge these both sections in one equations. So let's analyze it. First you need to calculate XU limit, and you can calculate easily, as the K value is the neutral axis, constant of neutral axis 0.484 Fe415. Similarly the different values given from IS code book. Similarly we need to calculate XU, right, for that one we need to equate C is equal to T. We have already calculated the C value, right. This one is for figure 1, right, C for figure 1, compressive force for figure 1. This one is for the compressive force for figure 2. Similarly this one AST Fy plus AST1 plus AST2. So from here you can easily calculate XU, and XU is the what you call neutral axis depth. From here you can easily calculate, then you will compare XU and XU limit. So XU, when it is equal to XU limit, then of course it will be bilane sections. If it is less than, then you under reinforce. It is XU is greater than, then it is over reinforcement. So moment of resistance for the T beams, we need to add both of them. That is moment of resistance in the compressive zone is equal to C1 plus C2. C1 plus C2. So we will add both on 0.36 FCK BW XU D minus 0.42 XU plus 0.446 FU. So if you add these both to then it will give for the compression zone and for the tensile zone. Similarly we have to add, right, T1 plus lever 1, right, for the temperature zone. You can, if you add the above equations, we have already calculated T1, right, for the tensile zone, right, in for figure 1 as well as for figure 2. So from here you can get the moment of resistance for the for the tension zone. So in conditions 2 we will see when it is not uniformly stressed. As I have told you, what do you mean by not uniformly stressed? As you can see here, stress block diagrams always start from the neutral axis, right. So as from these figures, as you can see here, the here up to here it is 0.02, right. So from here it is up to here it is parabolic, and from here it will be constant, and from the rectangular stress block distributions. So and this one is the depth of flanged, and imagine that I have taken one assumptions here from some portion from the rectangle and some portion from the parabolic. I have taken one imaginary lens and I have drawn a rectangular stress distributions, and this portion is a parabolic stress distributions, right. So from these ones I have named this figure as YF, right. Similarly then I have what I have did, I have up to this portion it is 3 by 7 XU, 4 by 7 XU. Same what I did in the previous lecture, I have separated figure 1, right, figure 1, this one is figure 2, and hope this one here C is equal to T, right? The total compressive force is equal to total tensile force in the figure same. So this one is Y, right? This one is BF minus BW, because total is what? BF. So we need to subtract the width of weave, so minus BW. 4 means satisfying C is equal to T. We need to imagine, or we need to substitute, means steel bars, right, so that it can satisfy. Right, here the Y is equal to 0.15 XU plus 0.65 means DF. So the means it is same as the previous ones. So from figure 1 it will be the same, right? Everything will be same because we have already calculated for the means wave. So 0.36 FCK BW XU T1 a lever 1. So we will calculate moment of resistance in the means compression zone and moment of resistance in the tensile zone. Now for the figure 2, let's see for the figure 2. Here my dear friends, the only difference is that instead of in the DF, always remember, instead of DF we'll only substitute, instead of DF we'll just substitute what? YF. So that is the only difference, because means YF is here, YF is assumed to be, that is means stressed, means types of means what we call distributions. So as you can see 0.36 FCK BF minus BW A to YF, because we have taken YF as the main criteria instead of DF. In the means what we call in the previous means in the previous topics we have taken DF as the main criteria. So T2 0.87. So here means what you call sliver arm will be D minus DF by 2 in the previous, but here D minus YF by 2. So if you substitute all these things, right, moment of resistance, right, moment of resistance, similarly for the total moment of resistance of T beams we will means add this one C1 plus C2, and for the T1 plus T2, if you substitute these ones it will give the moment of resistance for the whole T sections. So let's calculate for the XU, and hope you know how to calculate XU. It means XU limit, right, means and the means depth of neutral axis C is equal to T. We know that from the means C1 plus C2, right, C1 plus C2, similarly T1 plus T2. Similarly we need to compare XU and XU limit. So and at the same time moment of resistance, if you means this one is for the compressive zone, right. So moment means if you add C1 plus C2, right, C1 plus C2, that is means compressive force from the figure 1 to the compressive force from the figure 2, then you will get the total moment of resistance for the flanged beam, right. So hope you understood the, sorry my dear friends, hope you understood the means what equals the concept of flanged beam or the analysis of flanged beam. If you really like my video, please don't forget to share it to your friends. Thank you. Take care of yourself. Bye bye.